In your car right now, 50 to 150 ECUs are talking simultaneously on the same wire. The engine ECU, ABS module, the instrument cluster, the airbag controller, and many more. All of them sharing a single CAN bus. All of them transmitting whenever they have data. No central controller, no traffic manager, neither any scheduler. And it, not one single collision ever happens. Do you ever realize how this happens? And the answer is canvas arbitration, a mechanism so elegant it has been running in every vehicle since 1986 and it works without a single dedicated arbitration circuit. But by the end of this video, you'll be understanding exactly how it's work at the bit level and you'll be able to answer this question in every automotive interview. Two ECUs transmitting at the exact same microsecond. What happens? Let's see. Now, before we talk about arbitration, you need to understand two things about CAN bus physics. First thing, canvas is a shared medium. Every ECU is connected to the same two wire, CAN high and CAN low. When any ECU transmit, every single ECU on the bus see that transmission. Second, and this is the key to everything. Canvas has two states, dominant and recessive. A dominant bit is a logic 0. CAN high is pulled to 3.5 volt. CAN low is pulled to 1.5 volt. The differential voltage is 2 volt. A recessive bit is a logic 1. Both lines sit in 2.5 volt. Differential voltage is 0. Here is the rule that makes arbitration possible. Dominant always overrides recessive. If one ECU derives a dominant bit and another ECU simultaneously derives a recessive bit, the bus shows dominant bit. The recessive transmission is silently overridden. The transmitting ECU does not know this happened. This is called wired AND logic. The bus is the AND gate, dominant wins always. Keep that rule in your head. Everything else follows from it. Every CAN message has an identifier. In standard CAN, 11 bits, in extended CAN, 29 bits. This identifier does two things. It identifies the message content, engine speed, wheel speed, battery voltage, and it determines priority during arbitration. Lower numerical ID equals high priority. ID 000 bit is the highest priority message possible on any canvas. Why? Because 0 in binary is a dominant bit and dominants win. ID 000 is 11 dominant bit. Nothing can override it. ID 7FF 11 recessive bits is the lowest priority message possible. Look at this example. The ABS module has ID 0C0. The instrument cluster has ID 3A0. If both transmit simultaneously, the ABS module wins every time without any negotiation, without any acknowledgement. The physics of the bus decides it automatically. This is why automotive engineers assign lower ID to safety critical messages. ABS, airbag, deployment, engine torque request. These messages must win arbitration against any non safety message. When you design a CAN database or DBC file, ID assignment is a safety critical engineering decision. Press show priority table to see how real automotive systems assign ID by safety function. Now let's see an example of live arbitration. Now let's watch arbitration happens bit by bit. I have set up two ECUs, the engine ECU with ID 0C0 and the Havoc ECU with ID with ID 3A0. Both are ready to transmit. Both detect the bus is idle. The standard three recessive beats that signals end of the frame. Both start transmitting at exact the same moment. Now, let's see an example of live arbitration. Now let's watch arbitration happens bit by bit. I have set up two ECUs, the engine ECU with ID 0C0 and the Havoc ECU with ID 3A0. Both are ready to transmit. Both detect the bus is idle. The standard three recessive beats that signals end of the frame. Both start transmitting at exact the same moment. Press start arbitration. Watch the bit 0. Start of frame. Both ECU transmit dominant. Bus is dominant. Both ECU sees their own transmitted bit reflected back. They agree. Transmission continues. Bit 1 through 3, both ID start with 0 dominant but stay dominant. Both ECUs still agree. Now bit 4, engine ECU ID 0C0 in binary is 00011000000. Bit 4 is 1 recessive. Havoc ECU ID 3A0 in binary is 0 1 1 1 0 1 0 0 0 0. Bit 4 is 1, also recessive, still agreeing and continue. Now bit 5. Engine ECU transmit 1 recessive. Havoc ECU transmit 1 recessive. Still agreeing. Bit 6. Engine ECU transmit 1 recessive. Havoc ECU transmits 1 recessive. Bit 7, engine ECU transmit 0 dominant. Havoc ECU also 0 dominant. Wait, watch this bit carefully. Bit 8, engine ECU transmits 0 dominant. Havoc ECU transmit 1 recessive. The bus goes dominant. The Havoc ECU reads the bus. It transmitted recessive 1. The bus shows dominate 0. These do not match. The Havoc ECU stopped transmitting immediately. It's because a receiver. It logs a lost arbitration event. It will try again after the current frame ends. The engine ECU continued. It transmit dominant. The bus shows dominant. They matched. It keeps going. It been arbitration without knowing a collision even happened. That is CAN bus arbitration. No destructive, lossless, automatic, no retransmission needed. The losing ECU simply backs off and wait. Now, let's see a 3 ECU scenario. One collision is easy to understand. What about 3 ECUs transmitting simultaneously? Press 3 ECU demo. ABS module ID 0C0, engine ECU ID 180, dashboard ID 3A0. All three start transmitting at the same time. The arbitration plays out bit by bit as before. But now watch carefully. The dashboard drops out first at bit 4 when its ID diverges. Then the engine ECU drops out at bit 8 when its ID diverges from the ABS module. ABS bin. The dashboard and engine ECU both become receivers. Here is an important point. Neither the dashboard nor the engine ECU retransmits during this frame. They wait for the end of frame. Three recessive bits, then both attempt transmitting again. Now what happened? Engine ECU ID 180, dashboard ID 3A0. Same process, engine ECU wins. After that frame, dashboard get its turn. Three ECUs, three transmission, all successful, no collision, no data loss, no central coordinator. The total latency measured in microsecond. A 50 kbs. A standard CAN frame takes about 130 microseconds. Three back-to-back frames takes less than 400 microseconds. Your ABS module's message get through in 130 microseconds. Every time, regardless of what else is transmitting. In practice, an automotive CAN bus carries 20 to 50% bus load during the normal operation. That means the bus is busy 20 to 50% of the time. Use the bus load calculator. Enter message count, data length, and then cycle time for your typical ECU setup. At 500 kbps with 30 messages cycling every 10 milliseconds, you are at roughly 35% bus load comfortably. Push it above 70% and you start seeing latency issue. Lower priority messages are repeatedly losing arbitration and waiting. At 90%, a safety critical message can still get through immediately, but a dashboard update might wait hundreds of milliseconds. This is why CAN-FD was developed. Not just more bandwidth, but the ability to carry larger payloads so that individual messages take up less bus time. The arbitration mechanism itself identical in CAN-FD. Same dominant recessive logic, same wired and physics. CAN-FD is faster in the data phase but still use the same low speed arbitration phase for ID comparison. Now, after understanding CAN arbitration, let's see few of the important interview question and answer. Here are 6 important interview questions which are really important for any CAN bus arbitration related interviews. First one, two ECU transmit at exactly the same time. What happened? And the answer is non-destructive bitwise arbitration. Both ECU transmit their IDs simultaneously. They monitor the bus while transmitting. When one ECU detects a mismatch, it transmitted recessives but shows dominant. It stops immediately and becomes receiver. The other ECU continues. No data is lost, no error frame is generated. The losing ECU retransmit after end of the frame. Question 2. Why does the lower CAN ID means higher priority? And the answer is because a lower ID value has more dominant bits, 0 bits, in the most significant position. Dominance override recessive on the bus. The ECU with more leading zeros will always wins arbitration because its dominant bits will override the recessive bits of higher ID transmission. The next question is, what is the highest priority message on the CAN bus? And the answer is ID 000 in standard CAN, 11 0 bits. 11 consecutive dominance bit, nothing can override it. In practical, ID 000 is reserved and almost never used. Safety critical message typically uses ID in between 1 to 100 range. Now the next one is, what happens if two ECUs have the same CAN IDs? Both transmit, both monitor, both see matching bits all the way through the ID phase. Both enter the data phase simultaneously. Their data field will almost certainly differ at the same bit. And that point, both ECUs see a mismatch. Both generate error frame, both enter error active state. The bus sees an error condition. This is the DVC database design error. Duplicate ID must never exist on the same CAN bus. Now the fifth question is, does CAN FD use the same arbitration mechanism? And the answer is yes. CAN FD uses identical bitwise arbitration in arbitration phase, the 11-bit or 29-bit ID comparison. Only the data phase switches to the higher baud rate. The arbitration phase always run at the standard CAN speed, typically 500 kbps, to ensure the same wired and physics apply correctly across cable lengths and termination configuration. And the last question is, how does the transmitting ECU knows it won the arbitration? And the answer is, it does not explicitly know it won. It simply continue transmitting because every bit it transmit matches what it read back from the bus. If at any point it reads a different bit than it transmitted, it lost arbitration and back off. Winning is defined by the absence of a mismatch throughout the entire ID field. CAN bus arbitration is one of the most elegant mechanism in embedded system engineering. 50 is used, one wire, no coordinator, no collision, every safety critical message get through. The rule to remember forever: dominant override recessive, lower ID wins. The losing ECU back off silently and tries again. The simulator is linked in the description. Walk through the live arbitration tab until you can predict which ECU wins before the animation finishes. That is the interview ready knowledge. In video 4, we are going to cover CAN frame structure, every field, every bit, and why each of them is existing. Subscribe to our channel to never miss any updates. Thanks for watching. See you next time. Till then, take care and bye.